Welcome to another session with Miss Taylor. Now we're going to talk about Lewis structures, and I'm going to go through some examples of everything you should know about them. So for our first structure, we're going to do a fairly simple one. We're going to do PCl3, so phosphorus trichloride. Now the first step in determining a Lewis structure is the number of electrons. And how do we know that? We look at our periodic table. Phosphorus is in group 15, so it's going to have 5, and there's only one of it. There are 3 chlorines. Chlorine is in group 17, so it has 7. So we have a total of 26 electrons. Remember that we are only talking about the valence electrons, the outermost ones. So next we have to determine who's the monkey in the middle. So our central atom is going to be the one that is least electronegative. So how do we know that? Well, we're supposed to know our periodic trends. And if you recall, your periodic trend for electronegativity is that it increases as you go across the period. And if you are looking at your periodic table right now, you should see that chlorine is to the right of phosphorus, therefore phosphorus is in the middle. Alright, so let's put phosphorus, and we're going to draw in our chlorines. Now, it does not matter really if you put chlorine up here or if you made them into a little triangle or whatever. It doesn't really matter. Alright, next we're going to draw in our bonds. Now, the first thing we're going to do is single bond each bonded atom to the central atom. And we do that by drawing dashes. Remember, a dash means 2 dots. And if you want to draw your 2 dots in there, that's fine. This is just my particular habit. Okay, so far we've used 2, 4, 6 electrons. We have 20 more to go, so let's keep counting. That's 8, 10, 12, 14, 16, 18, 20, 22, 24. So once you have bonded the bonded atoms to the central atom using single bonds, you fill the octets of your bonded atoms. But if you heard me counting, we only use 24 electrons. But we need 26. Okay, so what do you do with those extras? They go on the central atom. And now that we have used 26 electrons, all octets are satisfied. 8, 8, 8, and 8. Our structure is finished. If you're trying to identify molecular geometry, you could look at this as central atom with 3 bonded atoms on it and 1 lone pair. And that matches a handout that my students in particular have. But this particular shape is called trigonal pyramidal. If you could envision it in 3 dimensions, it's sort of like a tripod, because you have to remember that lone pairs are space hogs. So you sort of have a balloon right here, and it's going to push these 3 chlorines closer together rather than them being flat like the points of a triangle. And the bond angle on this is 107.3 degrees. Good stuff. Let's do another one. For our next structure, we're going to do something that's going to require multiple bonds. Good old carbon dioxide. So carbon has 4, but there's only 1 of it. There are 2 oxygens, and each oxygen is bringing 6 valence electrons to the table. So 12 and 4 gives us 16. Okay, so who is in the middle? The least electronegative, but we can also remember that if carbon is present, it is in the middle. Okay, so carbon, an oxygen, and an oxygen. Alright, so we start by single bonding. Then we're going to keep counting. So 2, 4, 6, 8, 10, 12, 14, 16. Uh-oh, we're not done. Poor carbon in the middle only has 4 electrons. and it needs 8. So what we're going to end up doing is moving a pair from each oxygen to the middle. So what our structure ends up looking like double bonded carbon, one on each side, and 2 lone pairs on each oxygen. Now, carbon's a central atom, and your molecular geometry is centered around your central atom. So you've got 2 bonded atoms, no lone pairs, so this is AX2, which means it's going to be linear. And the farthest away they can get from each other is 180 degrees. All right, another example. There are some exceptions to the octet rule. We're going to look at one. Beryllium chloride. Right? Beryllium brings 2 electrons to the table, and each chlorine brings 7. So 14 and 2, 16. Okay, beryllium or chlorine. Beryllium is going to be the less electronegative one because it is farther to the left of the periodic table. So we shall place beryllium in the middle and a chlorine on each side. And we will start by single bonding. So that's 2, 4. Now we fill the octets of our bonded atoms. So we're up to 6, 8, 10, 12, 14, 16 electrons. Now, you're going, but wait, previously that didn't work. Well, beryllium is weird. Beryllium only needs 4 electrons. So this structure is actually finished. And again, just like carbon dioxide, it would be an AX2, so that means it is linear and 180 degrees. What are the other exceptions to the octet rule? Well, hydrogen, because it only wants 2. It can only hold 2 because of its size. And boron, which only wants 6. I'm going to show you one more exception to the octet rule. That's ICl3, or iodine trichloride. So iodine has 7, of course there's only one of it, and then each chlorine has 7, so we're looking at 28 electrons. Now, iodine versus chlorine. Who is going to be less electronegative? Well, electronegativity decreases as you go down the period, and iodine is lower, so iodine will be in the center. Chlorine, chlorine. Okay, so as usual, we start by single bonding. That used up 6 of the 28 electrons. Let's keep counting. 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, we've only used up 24 of the 28 electrons. What do we do with the other ones? If you have any leftover electrons, they go on to the central atom. And yes, I know that is weird, but this is an example of an expanded octet. Fancy way of saying the central atom has more than 8 electrons, and it's only okay on the central atom. So the shape of this particular molecule is skewed by these 2 lone pairs of electrons, and the formula for its shape is AX3E2, and its name is T-shaped, because in reality all you see is the T-shaped molecule, and bond angle would be 90 degrees because there's 90 degrees from one chlorine to the next. So that covers all the possibilities. Hopefully this will help you in your endeavors to draw beautiful Lewis structures.